This content is brought to you by BEC Financial Technologies, developing and operating IT for Danish banks.
Hello everybody, I'm very happy to be with you today. It's a privilege for me to talk about my project, my open project. It is open to all volunteers who want to eventually join our project. So I'm especially happy to have in front of me so many experts in IT. Oops. So what are the goals of the project? Just like that, we want to improve the quality of software. And at the same time, as a side effect, to lower the cost of program testing and maintenance. Better quality, you don't need to spend that much money for testing and even less for maintenance. There are essentially three ways of caring about program quality. One is, of course, testing. The second is proving programs correct on the basis of a mathematical theory. And the third is build programs correct, rather than build them anyway and then prove them correct later on. Testing is cost intensive, you know it very well. And besides, testing will never give you a guarantee that there are no more bugs in the program. Testing only allows you to discover the bugs, to remove these bugs, and usually when you remove one bug, you introduce three others in different places which you have to then locate by yourself. Proving programs correct is a theory developed since probably Alan Turing, who published the first paper on that subject in 1948, but the paper has been forgotten then. Later on, Hoare, Dijkstra, and other people were, and also myself, were tackling with the problem of proving, mathematically proving that the program is correct. And this area, as a theoretical research area, is developing quite well, but it never came to practice. And in my opinion, there are two reasons for this fact. One is that proofs are usually longer than theorems. Okay? You agree on that? And a theorem about correctness of program is longer than the program itself. So the proof must be a few more times longer than the program, and this is rather discouraging for proving programs correct, real programs correct. But there is another reason which is even more important. These programs that you want to prove correct are not correct. Programs that are coming out from the coding department, they are going to testing department, they are not correct. So the idea of proving programs correct was based on an expectation that we sit to the program, we try to prove it correct, we can't prove it correct, and in this way we find an error in the program, we fix the error, and we try to prove it correct again and again, and this never came to practice because this way of treating program correctness or program reliability was not very effective. And the third way, and this is the one that I'm trying to develop in my project, or we are trying because I have some collaborators already, is to build programs correct. I mean, to develop the approach to program production similar to that of production bridges, airplanes, or dishwashers. We first make a project, a blueprint, certain calculations. Based on this project, we know that if we then make our product along the lines of the project, then the product will be correct, meaning will satisfy the expectations of the user. And this idea was, for the first time, suggested by Andrzej Blikle, a Dutch, very famous computer scientist, myself in '78, and recently, maybe for some of you, 2008 is not that recently. Anyway, in the new ages, in Daphne project, and the slogan is correct by construction. They believe that they build programs in such a way that they are correct. Our project, our slogan is proved by construction, and what is the difference I will tell you in a moment. Now, there are two aspects of program quality. Consistency of program specification with the expectations of the user, and consistency of the specification with the program, consistency of the program with the specification. This is, I believe at this moment, this may be the future area of Lingua project. So far, there is very little research in this field. We concentrate on the consistency of a program with its specification, and not because we believe that this is more important, but because we feel that we are experts in this area. But I'm looking forward for people who would like to cooperate with me in the development of this problem number 1. But we are at the moment in number 2. Now, what do we need to realize the goal of producing correct programs? Provably correct programs, mathematically correct programs. Well, in the first place, we need a programming language with a mathematical semantics, because otherwise you can't prove anything. So you must have a language with mathematical semantics, and based on that language, you have to define rules of construction that guarantee that constructed programs are correct, whatever it means. We need such rules, and we have to prove that the rules are sound, which means that if they are given correct programs, then they will return a correct program as a result. As far as the problem of programming language is concerned and its mathematical semantics, we have chosen so-called denotational semantics. They are operational, basically, there are 3 categories of semantics: operational, axiomatic, and denotational. We have chosen the denotational semantics, and the denotational semantics is a function which assigns meaning to programs. And it is denotational in the sense that it is compositional. Here you see this equation which says that the meaning of a compound program, of a program composed of 2 parts, may be described as a combination of their meanings. This means compositionality, okay? And here, once we have a language with mathematical semantics, we won't prove the correctness of our programs, but we have to prove the soundness of our rules. We have to prove sort of a meta-theorem, which says that if we are given, say, 2 programs that are correct, and if we put them together according to the rule, then the result will be correct. The problem is that the existing languages do not have denotational semantics, and in my opinion, they can't have a denotational semantics because they were constructed from syntax to denotations, to meanings. Syntax, when a new language is designed, syntax comes to the table first, and only then we start thinking what the syntax, what sort of meanings the syntax should express. In my opinion, this is why the existing programming languages can't have denotational semantics. You can't directly, in a direct way, write the denotational semantics for them. So we decided in the project to build our own language in such a way that it has denotational semantics. And we construct such a language starting from denotations, from the meaning. So we first decide what we are going to talk about, and only later how we are going to talk about, once we know already the world of meanings. So, when designing a programming language, and our language Lingua has been designed in this way, we first describe a world of meanings. They are traditionally called denotations, and practically all denotations are functions that are mapping memory states into memory states. They're transforming memory states, okay? So, and this world of meaning is described in our case in a meta language, Metasoft. Metasoft was developed in the Institute of Computer Science of the Polish Academy of Sciences, where I was employed at this time. And here is the majority, the main creation when you think about a new programming language. In this place, in the descriptions of meaning, you decide what sort of data you are going to have, what sort of types, what sort of control mechanism, etc., etc. Then, once the world of meanings is described, we derive syntax in such a way that the denotational semantics will exist. And this can be done half algorithmically, to a large extent algorithmically. There is a little creation in this place as well, but not too much indeed. And once we have the descriptions of both these words, of meanings and of syntax, we can algorithmically generate a definition of semantics, and this semantics is denotational. And this way of designing programming languages I call denotational engineering. And our experimental language Lingua has been designed in this way. Now, what is the state of the art of the project? We have a methodology of designing programming languages, which can be said to be from denotations to syntax, so the other way around compared to today's habits. Then we have a methodology of programming, which we call proved by construction. To express the difference between correct by construction, that is a guarantee given by Project Daphne, and proved by construction in Project Lingua. The situation with Daphne is such that they are using programming language without a mathematical semantics. The language is described in, well, like other languages, in plain English practically. And they have construction rules that they believe to be sound. They are not proving them. And the majority of them are probably sound. But you know that the devil is in the details. In our case, we have a full mathematical semantics of our language, and we have program construction rules that are proved to be sound. And therefore, I say that our slogan is proved by construction rather than correct by construction. Now, the language is statically typed. It is object-oriented. It has a sketch of API for SQL. Anyway, we know how to introduce the SQL machinery into our model. And it has concurrency. This is even more sketchy than SQL. It's a concurrency practically limited to Petri nets, but the denotational models for concurrency is a real challenge, and there is a lot to be done in this place. And error elaboration in the sense that whenever our program aborts, it always communicates to the user, to the programmer, what happens. So all abortions are followed by the display of an error message, say, on the screen. So there is a full elaboration analysis, error analysis in the program. And there is an experimental interpreter of a subset of this language without objects, written by my students. I gave 2 one-semester courses at WarsawJS University 2 and 3 years ago. And the project is documented, fully documented, in a book A Denotational Engineering of Programming Languages, book in statu nascendi, it's still modified, and it is available on my site. You can have it, of course, everything that is connected to the project is free of charge. Now, what is to be done in software as far as the project is concerned? Two ecosystems. First, an ecosystem for language designers. It should include sort of an intelligent editor of the meta-language MetaSoft, say in Visual Studio Code as an extension of Visual Studio Code. This is a rather obvious task. Second, a mechanism that transforms the description of denotations into a description of syntax. The description of denotations is a list of definitions of constructors of denotations, and the description of syntax is a grammar. It's a context-free grammar, or BNF written in sort of a BNF-like formalism. I call it equational grammars. Then a generator of parsers, which is a rather routine task, a generator of implementations, maybe compilers and interpreters, and last but not least, definitely not least, a generator of an ecosystem for a programmer of such a language. So what the ecosystem for a programmer should include? In the first place, in order to design or to implement such an ecosystem, we have to complete our language, the definition of the language. Because at this moment in the book, I describe, well, I give sort of a sketch how to define mathematically the mechanism of data, of types, of procedures, of classes and objects, etc. But in order to build a real ecosystem, this definition must be completed, and this, of course, requires a decision whether we want to have, at the first moment, of course, whether we want to have a universal programming language like Python or a domain-specific programming language. This decision is to be taken. Once we have the completed Lingua, we need an intelligent editor, again, maybe in Visual Studio Code. We need a constructor of programs which implements the rules for program construction. And now the rules are such that whenever, in the majority of rules, whenever we want to apply a rule, we have to prove a certain implication. Not to prove the correctness of programs that we are going to put together, but to prove a certain implication. I'm not going to tell you the details now, but the implication is, these implications, they are mathematically not very sophisticated, but they may be long. They may have many variables. I mean, the number of variables in such a formula may be comparable to the number of variables in a program, quite large, okay? So a specialist theorem prover would be nice. There are several theorem provers around. And of course, this is the task is, and it's not a trivial task, to adapt one of them, to choose and adapt one of them. And such a theorem prover should have some axioms of D theory. D theory is the theory of denotations. Some theorems developed from these axioms. And for every program that is being developed, a set of lemmas that describe properties of objects that are manipulated with the program, by the program. Now, an interpreter or compiler. And finally, some experiments have to be done in order to see to what extent our construction rules are complete, and probably they are not. And in the course of developing these experiments, the set of rules may be complete. Now, our goal is, at the moment, to build two ecosystems, one for a language designer and one for a programmer. And here we have a dilemma, chicken or egg dilemma. What was the first, an egg or a chicken? Translating it to our terms, we have the following choice. We may develop Lingua manually without an ecosystem, and then given this Lingua and its ecosystem, design an ecosystem for language designers in Lingua. So this would be a nice exercise to see whether Lingua is sufficiently powerful. But we can do, of course, the other way around. We can start with an ecosystem for language designer written in Python or Java or whatever, and then, using it, develop the first Lingua. This dilemma hasn't been solved so far, and of course I expect from my cooperators that we shall probably take a decision together. Now, what remains to be done in the theory? Quite a lot, but I have to say that today the theory is rich enough to think about the first applications of the language. But of course, there is a lot of things to do in theory. There are models for script languages. Concurrency is a very large field. Polymorphic types, development of more practical program construction rules, domain-specific languages, which is a very promising area, etc., etc. This is not the end. And my last slide is about business perspectives, because I have a certain business perspective for my project. In the first place, I have to confess that I'm currently developing this project in an informal way and without any budget, by volunteers. But coming to a monetization of the project, I see a future, say, startup as an organization that is offering Lingua and ecosystems free for public. Access free for everybody, source free for a limited group, because, I mean, not everybody should jam in the sources which have a solid mathematical base. But available, the ecosystems available, open access for all. And monetization, possible monetization is like people who are installing Linux. Linux is free, so take it and implement it on your computer. No? I mean, if you are not somebody sitting in this room, you need help of a company that will charge you for that. So installation and maintenance tools, education, and finally, productions of reliable software. And that is the end of my talk, of the intuitive introduction of the talk. This presentation will be available to you. I have sent it to Piotr. You may write to me. You may see the technical details at the book, and the book from you may get it from my site. And the remaining part of the presentation, which I'm not going to show you, includes some examples, some technical examples, very, very simple, very toy examples. But if you want to feel what is the math, the idea, or the philosophy behind the project, then you can see it. Thank you very much for your attention.
Thank you so much, Professor. Does anyone have a question? I've seen some people raising hands even during the talk. So, yes, please, that gentleman.
Yes?
You'll receive give me a second. So, as you receive the microphone.
Yes, so I had a question like on the beginning, because there was a quality of the code, and you show that is the testing, the proof that the code is correct, and the construction of the code. And
The ways of,
constructing the code.
Yes.
So you mathematically prove that the code, like syntax or the code, which way it's writing is correct.
not syntax, that its denotation is correct.
Oh.
Its functioning is correct, because syntax, this is the job that the parser is doing. So correctness of syntax is easy. This problem has been solved for years.
So isn't that included in the previous one? Like in the testing, we try to prove that what we put into the function, for example, and the output is what it should be, like what we expect. So we test that the function is doing something correct. Then we mathematically prove that the function is working, so it's calculating in a way which have to be calculated.
What do you mean by we?
Like,
We are first testing, I understand, but we are then proving who? Who is proving after testing?
I mean, like developer is like you get the.
I haven't seen such developers who would ever prove the correctness of their programs.
I mean, like you build the calculator for the bank, and you have the specification.
Yes.
And based on the specification, you implement the function. And thanks to tests, we actually know that what we put and what we get is correct, but the value we are proving by analyze the specification. So now what is the construction? If it's not testing the syntax, like what is testing? Like what is proving in the construction object? What was this?
So you ask me what I mean by proving a program correctness, yes?
The construction, like the code.
Well, program which is a code, which is a piece of code, okay? And the piece of code has to obey to certain syntactical rules, and this is checked by parser, by syntactical analyzer. But then your program may do things that you do not expect to. It may be correct, syntactically correct, but instead of putting money from one bank account to another bank account, it will shift this money from a bank account of a customer to the bank account of the programmer. I mean, the program is working correct, but it's not working according to the expectations of the user, who is the bank. And I mean, by proving correctness of programs, I mean that, I'm not explaining this on the technical base, but I explain the intuition. I mean to prove that the program really satisfies the expectations of the user. So, for instance, that the balance sheets are always balanced. Once a bank operation is completed.
We have another question over
Yes.
there. Yes, please wait for a microphone. Thanks.
So allow me to say that I really enjoyed the presentation, and now let's get down to it. So I'm a big fan personally of correctness by construction. I think it's the most promising of the techniques. So total agreement here. Now, as no doubt you're aware, all the rage lately has been so-called artificial intelligence or machine learning. But a huge downside of what we use large language models today for when it comes to program construction, or basically it's being touted as replacing senior programmers with machines, which is not happening realistically this year or the next. But the denotational part, I think, is showing a lot of promise. And I'd like to know your opinion. What do you think of the applicability of machine learning to the construction of programs where they're built up from correct parts to a correct whole, using techniques that we use today for generating programs from scratch, either by genetic programming or by large language models?
Well, as far as AI is concerned, I have so far only one project that is starting within the Lingua project. and which I think is quite well tailored for the expectations that we may have with AI. Namely, AI shall try to train an AI to write a programmer's manual given a formal definition of the language. And I think in this respect, we may expect AI to do the job. But of course, I'm frequently asked the question whether the fact that AIs are now generating programs does not mean that the project is not necessary. AI will do it for us. But we must not forget that AI is trained on some knowledge basis. And if we want AI to write correct programs, we have to train it in some methods, and these are the methods. Now, in this project, AI is not necessary in the sense that the methods, they are algorithmic, and therefore what I mentioned here a constructor of programs, the second line. Okay, so this would be quote unquote the AI of the system, because the constructor of programs will be written in such a way that given 2 programs or 3 programs and proving a certain relatively simple implication, and this implication may be proved by AI, maybe, but so far I would not rely too much on AI because we know they like to confabulate sometimes. Anyway, this may be sort of an AI that you mean.
Lovely. Do we have any more questions for the professor? It seems like we have exhausted all the questions.
Thank you very much again.
Yes, please give a hand once again. It was lovely.